Hi, so here's something interesting. A few weeks ago, I was driving on this highway, and it was pouring, and the rain, smashing into my windshield, got me wondering, are these collisions with all these water drops slowing me down? Specifically, I'm asking if the collisions with the raindrops produce a substantial backwards force on a driving car. For this comparison, I want to compare the force from these collisions to the force the car experiences due to air friction. I do this comparison because it is known that air friction is a substantial player in car drag. It's commonly known that air drag goes like v squared. This can be shown via hand waving to be because the drag is the product of two factors. The first being the amount of air being pushed by the car times the other, which is the final velocity of the air after being pushed by the car. Both are linear in car's speed. Thus, their product results in the v-squared power law. For the exact same reason, the drag associated with the rain is also proportional to v squared. Just replace air with water droplets everywhere. So it turns out that the force from the collision with the droplets is very similar to the drag force from air. Further analysis shows that for the same reason, the air drag coefficient is also very similar to the rain's drag coefficient. Specifically, we get the following expressions. Note that as shown before, the drag forces are proportional to v squared. Also note that unsurprisingly, the drag forces are proportional to the densities of the mediums into which the car is colliding. But what does density of rain mean? Well, imagine a frozen instant in time. In this frozen instant, the rain is still. Now take an imaginary unit volume. The density of the rain is the total mass of all the raindrops in this unit volume divided by the size of the volume. Okay, so we want to compare these two forces. Let's take the ratio and denote it with alpha. And if we substitute with the expressions, we get this. Note that alpha is mostly a function of the ratio of the densities. So the challenge is to find the density of rain in relation to the density of air. This is non-trivial because the density of water is 1,000 times that of air, but the water droplets in the rain are relatively sparse. Sadly, measuring the mass of the rain in a unit volume that's frozen in time sounds hard, and to my knowledge no one performed any direct measurement of this. Thus, to answer this question, we need to do some working out. On the other hand, it is incredibly common to measure the mass flux per unit area of the rain. This is called the rain's intensity. Denote this flux by I. The flux is the mass of the water that passes through the unit area in some unit time. We can find the density of the rain from the flux with the fact that the flux is equal to the density of the rain times the raindrop's speed. This can be easily rearranged to give an expression that gives the rain's density from the rain's flux. Now, we need some rain data in order to find out if this force is meaningful. But before we dive deep into a rabbit hole of rain statistics, it's a good idea to start by looking for an upper bound. So let's calculate out alpha for the scenario where alpha is as big as possible, meaning the scenario where the rain is hard. So let's start by finding what could be an overkill value for rain intensity. I went to the US National Weather Service's website and found this table. This table is called a point precipitation frequency table, and it is used to estimate flooding rates and shows how likely different precipitation occurrences are. This table is in relation to New York. Regrettably, for some reason, this table is in inches per hour. In any case, let's take this cell that I marked in red. This cell means that the rain intensity written here is so strong that a 15-minute rain interval that will collect at least 1.47 inches of water is so rare that it is expected to occur only once every 50 years. To me, this seems like a pretty overkill value for the rain intensity. Converting this and doing the math results in 2.5 millimeters per minute of rain. To make sure this entry is overkill, you can look up rain in Wikipedia and find that any rain with intensity that is higher than 50 millimeters per hour is classified as violent rain. After conversion, this means that any rain that is more intense than 1 millimeter per minute is violent. In order to acquire the density of the rain, we also need to know the velocity of the raindrops. Now, although the velocity itself depends on the droplet size, which in turn depends on a bunch of things including the rain's intensity, this value can be given the upper bound of 10 meters per second. When you do the math of the rain intensity and velocity, the density of the rain ends up being 4 grams per cubic meter. In comparison, air has a density of 1 kilogram per cubic meter. This means that the density of the hardest rain New York could experience in 50 years is 200 times smaller than the density of air. If we take this result and add the drag coefficient, then to no one's surprise, the drag coefficient changes almost nothing, so the drag from the raindrops is completely negligible. It would probably be good to note here that I only talk about drag associated with a car hitting the raindrops. Cars that drive through rain probably experience major drag forces that have to do with the wheels being wet or driving into puddles. Going into this, I was aware raindrops are sparse, but water is so much denser than air, I thought the two might cancel out and give some comparable result. To my surprise, this turns out to never be the case, and the sparseness of the rain wins by a lot. To finish up, here's some insight to all the summer kids out there. Be more like your car. Hard rain might make you wet, but it should never drag you down.